Show of hands if you need a little more time to get anything down. Okay, and then just put your hands down when you are finished. Just while those people are getting stuff down, just a couple of notes. Let's see. The big thing is, I don't know if this is going to affect you guys or not, because I don't know how you do this, but the tutoring that I do on Wednesdays from 1:15 to 2:30, I'm still doing those. I'm just going to be changing the Zoom link on Google Classroom. So I don't, if you always get there through Google Classroom, then that won't make any difference. But if it's somehow saved or something like that through Zoom, you'll need to, again, get that link again through Google Classroom. Again, I will be changing that today or tomorrow. Okay, so it should show up in the next, for Wednesday. Okay, let's see. Other than that, I thought there was something else I wanted to tell you guys, but I don't remember what it was. Therefore, it must not have been important. We'll go with that. So again, once you've gotten the things down that you need, just put your hands down, and then we will continue. Today's lesson really isn't too bad. It does give students difficulty, but there's a couple core concepts. Like, I really feel like if you understand a couple core concepts to today's lesson, then it's really not a hard lesson. There's not a lot of like meat to it. So as you guys can see, we're going to be taking inverses, and you've seen inverses before. So just a kind of reminder, in the most like general sense, okay? In the most general sense, when we take the inverse of a function, all that means is that we're taking, so if I have two functions, I have a function f and I have function g. If g is the inverse of function f, all that means is we're taking all the domain values for f and it's becoming the range, and all the range values are becoming the domain. So we're basically switching the domain and range, and that's what it means to take the inverse of a function. Okay, so so that's just kind of keep that in mind. That's what it means to take the inverse. So let's go through and determine if these two functions are inverses of each other, using the fact that if we look at the composite, right, for these functions, if I take f and I evaluate it g, I should get out x. Or if I take g and evaluate it at f, I should get out x. If I get that thing, then what that tells me is these functions are inverses of each other. So let's look at that. Let's see for the first one. The first thing I'm going to do is this. I'm going to do f evaluated at g. Again, if these functions are inverses of each other, then this will be true. Give me 1 second. As always, I'm having a little bit of lag. Give me a second. Okay. So I'm going to do f of g of x, and then I'm going to have you do g of f of x. So again, one more time since it erased. If these two functions are inverses of each other, then this will be true. So let's check. So I'm going to take f, and I'm going to evaluate it at that. Okay, let's make that look neater, shall we? Let's make things look neat. Okay, so I'm going to evaluate that. And again, remember what it should do is it should produce x. So let's see what we get. So this is going to be, wherever I have x, just a reminder, wherever I have x, I'm going to be putting in this entire thing, right? That's how we evaluate this. So this is going to be 2 times something cubed minus 1. What is that thing being cubed? Oh, the stuff in the parentheses. So this good stuff. Okay. Before I continue, because that is kind of the key for this first part. Whoops, I see it. I see it. I know. I see it's moved over. That always drives me crazy. Okay. Hopefully you guys were able to see that. Are there any questions so far that you have? Okay, let's evaluate. So notice cube root, cube, those will cancel each other out. So we're going to end up getting, this is going to be equal to 2 times x plus 1 over 2 minus 1. Then our 2's are going to cancel out. Boom, boom. So we are going to get this equals x plus 1 minus 1, which equals x, which is what we said it should equal. Okay? So these two are inverse functions of each other. What I'd like you to do is I'd like you to show it from the other perspective. So I want you to show that g of f of x equals x. So why don't you do that, please? So same idea, but we're starting with g of x being the outer function, f of x being the inner. Okay, so if you would please, let's do that. Show of hands if you need more time. Okay, let's see what we got here. So I am just going to, they changed my app on me. So let's see how this goes. I almost feel like I have to relearn it here. So these are my functions. So let's see, we are going to do g of f of x. So again, we are going to be doing this. And again, it should produce x if they're inverses, which we already know they are. So let's see here. So I'm going to take g and I'm going to evaluate it at 2x cubed minus 1, which means I'm going to take this cube root function, and wherever I have x, I'm going to put in 2x cubed minus 1. Let's see, I just want to make sure I did that right. Did I do that right? So wherever we have, so we take g and wherever we have x, that should be right. So let's see what we get here. Okay, let's see what we get. So simplifying this, I get cube root, and getting rid of my parentheses, I get 2x cubed minus 1 plus 1 over 2. I think you guys would agree. The negative 1 and plus 1 cancel each other out, which gives me 2x cubed over 2. The 2's cancel each other out, so I get the cube root of x cubed, which equals x. So again, we have verified that these two functions are inverses of each other. Okay, and the way we did that is we took one function and evaluated at the other, and it produced x, specifically x. That's really important. That's all it can produce. Any questions on that? Does anybody need to get anything more down before we move on? No? Okay, let's keep on going. So this is a really important point. It's going to make, when we go to take, so basically here's kind of our goal today. Our goal is that you are going to be given a function f, and you are going to be asked to take its derivative, the derivative of the inverse function. And part of that, not always, but a lot of times what they'll do is they'll say, hey, look, I've got this function and it passes through this point. And it's really important to understand that if the original function passes through the point 3,5, then the inverse is going to pass through the point 5,3. That's a really big deal. Okay, which is why I highlighted this. It doesn't mean I'm not trying to say this is more important than anything else. I just really want to focus your attention here that it's an important idea when we go to take the derivative. Okay, so this is a big deal, and it's going to make your understanding really important. So just kind of keep this idea in mind. So again, if the original function contains a specific point, okay, so like 7,2, then the new function, the inverse, will contain the point 27. Okay, so keep that in mind. Does anybody need any more time getting down theorem 5.6? Okay, and again, when you are finished, put your hands down, please. Okay, so let's talk about the existence of an inverse. So these are kind of saying the same thing, 1 and 2. So so in part 1, they say a function has an inverse if and only if it's 1 to 1. Okay, that's actually, technically speaking, that's all you need to know. A function has an inverse if it is 1 to 1. What they do in part 2 is they're kind of clarifying that. Okay, and they're talking about a function being monotonic. We've talked a little bit about monotonic, but we'll talk about it in a little bit more in just a second. But I'll let you guys get this down. In regards to theorem 5.7, raise your hand if you need more time. While you guys are getting that down, then I am going to do this graph is going to be I'm going to make a graph of this. It's going to be inaccurate. In general, it'll be right, but again, it's not. Obviously, it's not perfect. And it's not meant to be. Okay, so let's talk again about what it means for a function to be 1 to 1. When a function's 1 to 1, what that means is for every domain value, there's one range. And for every range value, there's one domain. In other words, both things have got to be true. So here's what I mean. Let's give you guys, actually, even looking at this function right here. So this function that right here, this function right here, this is the graph of it. And it's actually, it is 1 to 1. And here's why it's 1 to 1. And normally we would verify this, but here's why it's 1 to 1. For every domain value, so for example, let's say, and I don't know these, again, these are completely made up points, so just kind of keep that in mind. So if x equals 2, right, then this y value, which I think is 10, so it goes through the point to 10, there's only one output. So in other words, when x equals 2, there's only one output. That output is 10. It's not like there's a second output of like 7, right? There's only one output. okay, then that's really important. So the first part of that thing is where for every domain value, there's one and only one range value. So again, when x equals 2, there's only one output, in this case specifically 10. The other part of that, for this function to have an inverse, is it says for every output. So for example, this is 10. For every output, there's one and only one input, right? So when y equals 10, there can only be one input, in this case specifically 2. So for example, for a function that is not, for a function whose inverse is not a function, right? We have a really easy one, and that is like y equals x squared. And the reason is, if you look at the function y equals x squared, again, you don't have to get this one down unless you want to. So for every input, there's one and only one output. So for example, if I plug in the number 2, the only output is 4, right? Because the only output is 2, 4. But, and this is important, for every output, there's more than one input, right? And what I mean by that, if I have an output of 4, right? So if I have this output of 4, there's actually two inputs that produce 4, and that is -2 and +2. Therefore, the function y equals x squared, its inverse is not a function. Okay? So that's all it means to be, that's all, when we talk about a function being one-to-one, that's all we mean. For every input, there's one output. For every output, there's one input. That's all we mean. Now, let's talk about a function being monotonic. Okay? Because monotonic is basically a description. Monotonic, when we talk about a function being monotonic, what we're really saying is over its domain, the function is either always increasing, as in this case, as we can see visually, it's always increasing, or it's always decreasing. It can't do both. A function that's monotonic cannot do both. So in other words, a monotonic function wouldn't go up for a bit, then go down, then go up. It has to always be going up or always be going down. It's got to make a choice. Okay? Any questions on either what it means to be one-to-one or what it means for a function to be monotonic? So the advantage of knowing if a function's monotonic is if a function's monotonic, it will be one-to-one. Okay? Every monotonic function is 1-to-1. Okay, so it takes care of it. Now, if I ask you, if I say, hey, is this function right here, is this function's inverse a function? Okay, so is this function's inverse a function? Then what we really want to know is it one-to-one? In other words, is it monotonic? And there's a couple of ways we could do it. One is we could graph it like I did here. And I can say, oh, it's always increasing, it's monotonic. Yep, its inverse is a function, great. But we can also do this through calculus. And what I'm going to do is I'm going to check to see, is it monotonic? I'm going to use calculus to do that. And the way I'm going to do that is I'm going to take the derivative. Now, my question is this derivative always positive or always negative? If it's one of those two things, then it's monotonic. And I think you guys would agree, there's no critical values. And even if there were, no matter what I put out of this, no matter what I put into this thing, I'm always going to get a positive number that's greater than or equal to 1, right? So this thing is, the derivative of this thing is always positive. What does that tell me? That means this function's always increasing. Therefore, it's monotonic, and therefore, the inverse of this function right here, the inverse is also a function. Okay, so notice how we can use derivatives to determine if a function is monotonic. So the question, one of the questions was, is every one-to-one function monotonic? And the answer is yes. Okay. Any questions on that? Anybody need more time before we look at another function?
So is the is the derivative the inverse function, or it
No,
just proves that there is one?
right. The second thing, it proves that in this case, when we take the derivative and then we check to see that that derivative is always positive or always negative, it's proving that there is one. I'll remind you guys how to do inverses in a minute. Okay, more than a minute, but I'll remind you guys how to take inverses. But taking the derivative is not taking the inverse. Okay, any other questions? Okay, let's look at this one. So first off, let's just look at the graph. Let's just look at the graph. So the graph is going to look like this. And I want you just to look at the graph. We're gonna kind of do this problem twice. We're gonna look at the graph, make our determination, and then we're gonna take the derivative and make our determination. So the graph looks, again, non-accurately, looks like this. So what I want you to determine is this function, just looking at it, does it appear to be monotonic, yes or no? If it's monotonic, then its inverse is a function. If it's not monotonic, then that is false. Its inverse is not a function. So in the chat, what I'd like you to do, if it is monotonic, type 1. If it is not monotonic, type 2. If you don't know, type 3. So 1, it's monotonic. 2, it's not monotonic. It's good so far. Got some people maybe not sure. Some people breaking the rules. Okay, let's see what we got here. So remember, a function is monotonic if it's always increasing or always decreasing. So let's look at this function. Increasing, oh, now it's decreasing and now it's increasing. It's not monotonic because it has to be doing always one or always the other. But this one increases, then it decreases. Boom, not monotonic. Okay, which tells me, and it tells you, that the inverse is not a function. Okay? Any questions on that? Okay, let's check it using calculus. Let's check it using calculus. Let's see if this thing, so we said it's not monotonic, therefore it's not a function. Let's look at calculus and have it back it up. So what I'd like you guys to do is take the derivative and let's see if the derivative is either always positive or always negative. Show of hands if you need more time taking the derivative and checking it. Okay, let's take our derivative and see what we got here. So in this case, I take my derivative, or I attempt to take my derivative. So let's see, f prime of x equals 3x squared minus 1. So I think you guys would agree this thing has critical numbers, which is okay. I want to emphasize having critical numbers isn't bad, but let's see what happens. So we have critical numbers. So 0 equals 3x squared minus 1. So 3x squared equals 1. X squared equals 1/3. X equals plus or minus the square root of 1/3. So if I were to put these in, so at negative 1 over root 3, 1 over 3, and at positive 1 over 3. So let's check and see what happens. So I think you guys would agree to the left of this, so if I put in like negative, let's say -3, this is a positive. If I plug in 0, I get a negative, and if I plug in, 3, I get a positive again. So what does this tell me? It tells me it's increasing, then it's decreasing, then it's increasing. Therefore, this thing's not monotonic, and therefore the inverse does not exist. Okay? So, it's not that the inverse doesn't exist, it's that the inverse is not a function. Again, we can take the inverse, but the inverse is not a function. Okay? So that's what this tells me. And again, the reason I want to emphasize, by the way, just finding critical values is not enough. And the reason I say that is you can have something that looks like this. We've seen this before. You can have a function that maybe does something like this. It pauses for a second and then it continues up. This is monotonic. I mean, I may not have drawn it looking monotonic, but it's monotonic. It hits 0 for a second. There's a pause, but then it continues increasing. That's fine. Okay. What's not fine is that it starts going back down. Okay. Any questions on letter B? Is everybody okay that the inverse of that function is not a function? Okay, again, what we're checking to see is the inverse a function? And our answer in this case was no, it is not. Any follow-ups on that before we move on? Okay, then let's talk about how you find an inverse. This is something that you have done before. I want to say that I've even done it with you. In fact, I'm pretty sure I have. It was a while ago, and I see that something got erased in example 3. So while you guys are getting that down, I'm going to fix example 3. There we are. So again, this is something that you've done before. Again, you have found the inverses of a function, and I'm going to kind of highlight the things that are really important. There really isn't something to highlight there. Checking in with you guys, show of hands if you need more time. Okay. So I'm going to give you, in general, there's a couple things where there's all these steps that you need to do. You don't really, there's only a couple things that you really need to do here. And if you do these couple things, you'll get it right. So first off, this is not as important as everything else, but you should do this. You should change that f of x to y. Okay, so you should write it like this. It will just make things a little bit easier. It's not a big deal, but it will make things easier. Now, in general, here's what needs to happen. One thing that has to happen at some point, and I usually do it, I usually make it the very first thing I do, is you need to switch x and y. And that literally means you're picking up x, you're picking up y, and you're switching them. So it looks like this. Okay, so again, the instructions didn't tell you to do it first, but again, at some point you have to do it. I always do it first. That's the very first thing I do. That's actually, you have taken the inverse at this point. The second you pick up x and you pick up y and you switch them, you've taken the inverse. From here on out, all we are going to do is solve for y. Okay, so y on one side, everything else on the other. So let's see, I'm going to cube both sides. X cubed equals 2y minus 3. Add 3 to both sides, so x cubed plus 3 equals 2y. If you don't mind, I'm going to rewrite. So this is, let's see, 1/2 x cubed plus 3 equals y. And then I'm just going to write it as the inverse. Again, this is just something we tend to do. We tend to put it in proper notation. And we get this. Okay? So the big things that I want you guys to keep in mind. There's really two big things you need to do. And the order in which you do them is not important. The first thing that needs to be done, at some point, you have to pick up x and you have to pick up y and you have to switch their place. Okay, at some point, you can take this function that what they're having you do is they have you solve it for x and then switch them. Doesn't matter. You can switch them at any time. I usually switch them right off the bat. I switch them for x and switch them for y, and then you then have to solve your function in terms of y. Okay, if you do those two things correctly, you'll have taken the inverse. Okay, now we're going to verify, we should verify that these two are inverses, and we'll do that in just a second. Did I? No, I didn't. Okay, so, but before I do that, are there any questions? Oh, wait a minute. I made a slight mistake. Let me fix that. I just noticed I don't know why I cubed both sides when I'm supposed to square both sides. So let me fix that. I just saw that. I don't know why I did that. I was supposed to I don't know why I thought it was a cube root. That was kind of weird. Let's just double check. So you square both sides, you get that. Yeah, that looks better. Yeah, I don't know why I cubed it. For some reason, I thought it was a cube root. Like in my mind, I was thinking that was a cube root. Okay. Before I continue, do you have any questions? Okay, so the next thing we should do is we should verify that we're correct. And again, the easiest way to verify that is the way we verify it's correct is you don't need to do this both ways, but you should do it one. So I'm going to take like f and evaluate it at f inverse. Okay, if it produces x, then I did it right. I'm good to go. So let's do that. So I'm going to take f, which was, what is f? F is the square root function. So f is the square root, let's see, of 2. Let's see here. What is x? X is 1/2 x squared plus 3 minus 3. Let's see if I did that right. I'm just going to double check myself here. Actually, I'm going to, if you don't mind, I'm going to show one extra step here because I usually do show this step. So give me just a sec. Okay, so let's see what we got here. Let me just make sure that I plugged everything in correctly. So it's 2 times x, and this is x. So that looks good, minus 3. Looks good. You're going to check one more time. Okay, so let's simplify that. So in this case, actually, why do I have that f now? That was weird. I think I meant to say f of x equals. Okay, let's check what we got here. So this equals, a lot of mistakes there. So this 2 and this 2 are going to cancel out. So I'm left with x squared plus 3 minus 3, which leaves me with the square root of x squared, which equals x. Boom, it equals x. That's exactly what I wanted. These two functions are inverses of each other. Okay? Any questions on that? Okay, let's look at this one. So this one's asking us, it's not asking us to find the inverse. What it's asking us to do instead is show that, first off, that the sine function's inverse is not a function. So we're going to show that it's not one-to-one. And then what we're asked to do is to verify, and this is important later on. I want to say it's important tomorrow, but maybe not. Probably not tomorrow. I don't remember where. My order of my lessons are a little bit off, so it's probably not tomorrow. But it is an important concept about this limited domain here. So I think you guys would agree. We could go through and take derivatives and things like that, but I don't really need to. I think you guys would agree. The sine function looks poorly drawn like this. So it kind of does this. Obviously, I've done a terrible job there. Okay. I see a question in the chat. I'm going to answer it in just a minute. Okay. But let me just finish this topic and then I will. So first off, I think you guys would agree this function, the sine function, is not monotonic because it's increasing, then it's decreasing, increasing, decreasing. In fact, it does that forever and ever. But if you notice, if we restrict the domain, right? If we restrict the domain specifically to negative pi over 2, so from here all the way to here, pi over 2, this restricted area, right? Just this little restricted piece, this function is increasing this entire time. Therefore, for that specific domain, from negative pi over 2 to pi over 2, it's monotonic, okay? So if I were to restrict the domain of the sine function, if I were to just say, okay, you know what? I'm going to look at the sine function, but only from negative pi over 2 or pi over 2. And I was going to say, if I restrict the domain, is the inverse a function? Yes, it is. As long as that domain is restricted. It's not a function for the entire domain of the sine function, but just for that piece, the inverse is a function. Again, we could move that, right? Instead of going from negative pi over 2 to pi over 2, what if I went from like pi over 2 to 3 pi over 2? Right? So to here, then I think you guys would agree. This is also monotonic. It's going down forever. It's going down over that period. So it's monotonic there. So a lot of times what we do is, in order to force a function, in order to kind of look at a function's inverse and make it a function, we restrict the domain to just one section, like in this case. Okay? And again, we're going to revisit that idea later on when we talk about inverse trigonometric functions. But that's all we're doing, is we're restricting the domain to a section where it's monotonic. Okay? It's something that we can do. Okay? Before I kind of go back, like I said, before I kind of go back and answer some of the questions that are being asked, in terms of this one, are there any questions? Sean, what do you got?
I was wondering why it asks you to show that it's the largest interval.
So the reason they're doing the largest interval, and again, we could take the derivative of this function and look at its critical numbers and show that it's largest. The reason they're doing that is when we go to do inverse functions later on, we're going to want to use the largest section where it's monotonic, right? Because I think you'd agree, I could have gone from like, let's say here to here, and this would be monotonic, but we're trying to, in this case, kind of identify what is that section that's the largest section. In this case, it goes from negative pi over 2 to pi over 2. Again, there's multiple, there's lots of, when we say largest, it just, there's lots of largest in this case, but we're looking for where it's monotonic. Does that make sense?
Yeah.
Okay, let's kind of go back really quickly. One of the questions was asked was, just because we check something one direction, so I check f of f evaluate the inverse, it produces x. Is it possible that if I took the inverse and I evaluated f, I might get something different? It really, so by definition, technically speaking, if we were, if I were asking you to prove this in like a higher level course, you really are supposed to check it both ways. Okay. I'm going to say, and I'm not going to say I'm 100% positive. I just can't think of any functions that I can't. The definition is very specific. It says you're supposed to check it both ways. You guys will not encounter a function that doesn't work in one direction. In other words, if I take f and I evaluate the inverse and I get x, the other way is going to work every single time. Now, will that always be true? I believe so, but I'm not going to say I am positive. There's a reason the definition is given. The definition is given so that we check it both ways. But again, I can't say that I've ever encountered a function that doesn't, but I don't want to say it doesn't. I don't want to say that it will never work, because then why would we have that definition, right? So for you guys, as long as you check it in one direction, and what I mean is either f evaluated f inverse or f inverse evaluated f, and you get out x, you're good to go. And like I said, I believe that will always be the case. But again, definition, like if you were to go later on and become a math major in college, they would want you to check it both ways. Okay, because that's the definition. Any other questions before we leave 3 or 4? Okay, so let's talk about this. I'll let you guys get this down. What is going on there? Why don't you guys also get theorem 5.9 down? That is a flashcard. It is an important one. Okay, it is an important flashcard. It comes up on AP all the time, every year. So it's really, and we'll talk about it. It's actually, the flashcard is more confusing than actually understanding the idea behind it. We'll talk about the idea behind it, and obviously after you guys have gotten a chance to get stuff down. Let's see, show of hands if you need more time. And again, just put your hands down when you are finished.
You have both theorems listed as.
You're breaking up really badly. Can you type that? I can't understand. I can't understand a word you're saying. Oh, I see what you're saying. Okay. You're right. This one is 5.8. Gotcha, gotcha, gotcha. Okay. So let's talk about just a few things on here. So as you guys can see, just to get again, quick summary. I know you already have this in your notes, but again, if the original function, so I'm going to just say original and inverse, So if the original function is continuous on its domain, then the inverse is continuous on its domain. Okay? If the original function is increasing, then the inverse function is increasing, and vice versa, right? Decreasing, then the inverse is decreasing. Okay? And the big part is that if it's differentiable on the interval containing C, then it's also the inverse is differentiable at C. This is the big part. This right here. Okay? Now I want to kind of talk about what's going on here, because this idea isn't so bad. It looks really bad. Like this is a flashcard that looks bad, but it's not. And here's what I mean by that. So let's say I have two functions, one function f and its inverse. So, and I'm going to make a quick graph of that. So, and again, I apologize. They're not going to, my graphing skills are always iffy. So let's say the original function f looks something like, I can do better than that. Let's say it looks something like this. Okay, so this is f. And importantly, maybe f contains the point, let's say 2, 5. And f prime of 2 equals, we'll say, I'm going to make this up. It's not correct, but we'll just say 3. Okay? Then, according to our flashcard and according to the things that came before, our inverse function, which might look something, again, I'll be off. Let's say the inverse function looks something like this. Okay? So a couple things about that inverse function. First off, from what I told you guys before, it has to contain the point 5, 2. That's a big deal, right? So remember how I originally told you guys that for every point AB, the inverse has to have the point BA. So the first thing it has to be, since this function contains the point 2, 5, the inverse function contains the point 5, 2. What this flashcard is actually telling us is that if the derivative of our original function equals at this point, if the derivative of this function at this point equals 3, then if we want to find the inverse, if I want to go and find the derivative of the inverse function, so if I want to go and find this, let's see how I always have a little trouble writing this. It's actually just going to be equal to the reciprocal of the original. In other words, if the slope of the tangent line at the point 2, 5 is equal to 3, then the slope of the tangent line to the inverse of the function is going to be equal to the reciprocal, 1/3. That's the thing to keep in mind, okay? That these two slopes are going to be reciprocals of each other. Okay, so if you know the slope of the tangent line through this point, then you know the slope of the tangent line through this point. Okay, if I told you the slope of the tangent line through this one was -7, you would know that this one would have to be -1/7. Okay, that's really the big idea here. If you understand that concept, then this is actually going to be fairly easy to do. We're going to look at an example in just a minute, but are there any clarifications yet? Okay, so let's look at an example. So I'll let you guys get down example 5. Okay, So let's go through how we do this. So the first thing is, and this is actually a really big deal. So again, I want you to think about what's kind of going on here. So again, I'm going to make up a graph that's not even close to the actual graph, but it kind of helps us visualize what's going on here. So if the original graph were to look something like this, it's going to pass through a point. It's going to pass through the point 3 something, okay? Which means the new graph, the inverse function, which maybe looks like this, is going to have to pass through the point something 3. Okay? So, with that being said, the first thing we're going to do is we're going to figure out what is our actual point that we're talking about, right? So for this, I'm going to take f. We know that x equals 3, so I'm just going to evaluate f of 3. And I get 1/4, 3 cubed, plus 3 minus 1, which is 27/4, plus 2. So that equals, let's see, 27/4 plus 8/4. It's too bad it's not nice. What is that? Looks like it is 35/4. Really, did it come out that badly, or did I just do something wrong? Let me double check myself. I almost feel like I've done something wrong. Or did I evaluate the wrong number? Oh, no, I wrote it down wrong. I see, I'm sorry. I'm sorry, I did make a mistake. I'm sorry, I did make a mistake. Let me fix it. I see what I did. I'm not answering the right question. Let's try it again. So boop, let's just I didn't look at the question close enough. They're asking, and I missed it, I apologize. I was asking, what is the inverse when x equals 3? Okay, that's a little bit different. Okay, so let's start again. So really what's being said here, let's go back to our question. What it's really saying is this. We have our two functions. Function 1, which is f, and function 2, which is f inverse. And what they're telling us in this case, and this is where I messed up, is they're saying, hey, look, you know that the inverse passes through 3. We don't know what the output is, which means, I think you guys would agree, the original function is going to pass through something, but its output is going to be 3. This, of course, is the original function. So what do? Well, we know the output is 3, so I'm going to set the function equal to 3. And then I am going to solve. Now, in this case, I might do a quick little guess and check. Let's see what happens. If I were to plug in like, I mean, again, just because it's a cube, I don't really want to try solving that. That might be rough. I might do it on a graphing calculator. That might not be so bad. But let's just check. Let's see if I plug in, let's plug in 2. The reason I chose 2 is that will make it, let's see if this is true. If I plug in 2, I get 3 equals 1/4, 2 cubed plus 2 minus 1. Let's see if that's true. So 1/4, 8 plus 2 minus 1. This is 2 plus 2 minus 1, which is 3. Yeah, 3 equals 3. So in other words, whoops, let me let this person in. Give me a sec. So in other words, this question mark right here equals 2, which means, right, that this is true. Okay, so again, I want you to notice, they told us, hey, the inverse passes through 3. So we had to figure out what was that other value. And I did that by just setting the original function, right? Since the input for the inverse was 3, that means the output had to be 3. So what did we put in to produce 3? Oh, we put in 2. Now, the question is, the second question is, what is the derivative of this function, of the inverse function? In other words, they want to know, what is the slope of the tangent line when x equals 3? What is the slope of that line? Well, I don't know what that function is, right? I can't just take the derivative and evaluate it because I have no idea. What is the inverse of this function? I have no idea. And not only that, it would be really hard to take the inverse. So what I'm going to do instead is I'm going to use the fact that the slopes are reciprocals of each other, right? Just like I told you guys before. So if I know the slope of this line right here, then I actually know the slope of this line right here. So let's do it. So I'm going to take, first off, I'm going to take the derivative of f of x. So f prime of x equals, 3/4 x squared plus 1. Then what am I going to evaluate it at? I'm going to evaluate it at 2. So f prime of 2 equals 3/4 times 2 squared plus 1. That's going to be, looks like it's 4, right? Yep, it equals 4. So what does that tell me? What must be the slope of the tangent line to this graph? So in other words, what must be f, the derivative at 3? Well, it has to be equal to the reciprocal of this. So in other words, it has to be the reciprocal of this, which is 1/4. So again, the key, I really want to emphasize this to you. This concept is not hard as long as you understand two important things. Thing number one, for every point on the original graph, we have the opposite, right? So if I have the point AB on the original graph, we have the point BA on the inverse graph. Okay, that's important thing number one. Important thing number two, if I know the slope of the tangent line to one of the functions, then I know the slope of the tangent line to the other function at that, that other point, right? So if I know the slope of the tangent line at 2, 3, then I know the slope of the tangent line to 3, 2. They're reciprocals of each other. Okay? Questions on that? I'm going to want to give you guys one to try, if I can find one. But are there any questions on that? Okay, let's see if I can find one. Okay, let's do this. I'm going to do this down here. So we have this function f of x, and it equals x cubed plus 2x minus 1. And what we are going to be asked to do is we are going to be asked to find the derivative of the inverse at 2. So they're asking us, what is the derivative of the inverse function when x equals 2? So remember, there's two parts to this. And I'm going to talk you through it a little bit, just again to kind of help you out. So if the original function looks like this, notice all my functions always look the same. I'm very uncreative. So if the original function looks like this, then this is the this is the inverse function. We are being told right now, right? They have given us this point. It is 2 something. And what they want to know is, what is the slope of the tangent line when x equals 2 to that graph? Okay, so you need to know a couple things. One, you need to go, basically the big thing that you need to do is you need to know what is the derivative at this point right here, which is the point question mark 2. What is that derivative? See what you can do. Again, notice how I don't need a flashcard. As long as I understand that concept, I am good to go. Show of hands if you need a little more time. Okay, so let's see what we got. So the first thing I'm going to need to do is I need to figure out, as you guys know, I need to figure out what is this question mark. And the way I'm going to do that is I'm going to use this. I'm going to take my original function and set it equal to 2, right? Because I know the output is supposed to be 2. So I'm going to say 2 equals x cubed plus 2x minus 1. And now I'm going to figure out what is that value for x. And again, just doing some quick guess and check, I'll probably find it pretty quickly. So for example, it looks to me that it's probably 1. Let's check. 1 cubed is 1, plus 2 is 3. 3 minus 1 is 2. It's 1. So in other words, I now know that this question mark right here for both of these is 1. Okay? Why is that important? Because now what I'm going to do is I'm going to take the derivative of this function right here, and I'm going to evaluate it at 1, because it's going to give me the slope of the tangent line at the point 1, 2, and that will allow me to figure out what this is, because it will just be the reciprocal. So let's do it. So f prime of x is 3x squared plus 2. I'm going to evaluate that at 1, so f of 1 equals 3 plus 2, or 5. Therefore, the derivative of the inverse function, right? I don't even have to do any math. Look how easy. Well, okay, I have to do a little bit of math. I know what this is right off the bat, right? It has to be equal to the reciprocal, 1/5. Easy peasy. Any follow-ups on that? That's really, I'll be honest with you, that's the big idea today. If you get that, you really get that's the big concept. That's really the big concept. That's the concept that really comes up on the AP. Okay, and it comes up quite a bit. Any follow-ups? I have one more example I want to look at. Okay. If not, then I want to just kind of show you guys a couple little things on this. Give me 1 second. Am I forgetting something? I am forgetting something. So I'll let you guys get this down. Let me add a line to this. So one of the questions was on the AP exam, will they do guess and check? Actually, they even do it a little bit easier. So what they'll do on the AP exam is they'll say something like, they'll make it even easier. And again, I don't remember exactly. I'm going to apologize because I don't know the normal wording. And of course, it can change from year to year. But usually the way this appears is they'll say, hey, the function f of x equals, or the function f of x passes through the point, let's say 1, 2. And it has a derivative of, they say the derivative of f of 1 equals 7. Then they'll say, what is the derivative of this? And you just need to know how that flashcard works. And you say, oh, it's 1/7. So they don't even really, it's usually, they don't really give you a function. It's more of like, what they do is they do it in general terms. Something like this, where no function's even ever given. It usually shows up on the multiple choice. I don't think I've ever seen it on the free response, though maybe I'm wrong. Okay. So let's talk about this last example here. Let me get this stuff out of the way. Move over there. So it's just, it's something that it's good to know. So notice what happens. So I have these, I have the function f of x equals x squared and the square root of x. Notice what happens. If I take f of x and I evaluate it at 2, right? I think you guys would agree I of course get 4, right? If I take the derivative, sorry, if I take the inverse function and I evaluate it at 4, right, I get 2. If you notice, we're asked to show the reciprocals of each other. And the way we can do that, let's look at the slopes of each of these functions. Okay, so let's look at the slope of f of x evaluated at 2. So f prime of x, I think you guys would agree, equals 2x. If we evaluate that at 2, right? If we evaluate that at 2, we get 4. On the other hand, if we take the other function, so this is our inverse function, right? And we take its derivative, which is 1 over 2 root x, and we evaluate it at 4, we get 1 over 4. And notice if we multiply those numbers together, we get 1, which shouldn't surprise us, right? I already told you guys that those slopes were reciprocals of each other, right? So if the derivative of the original function is 1/7, then the new one is 7. We multiply those together because our reciprocals are always going to equal 1. And we can check that for this too. So this is just kind of emphasizing the fact that those two slopes are reciprocals of each other. And I just really want to emphasize that, because if you understand that the original function and its inverse, their slopes are reciprocals of each other, the flashcard itself is a lot easier. Okay? Any follow-ups on that? No? Okay, then that's what I have for you guys today. If you want to stick around and ask any questions, you're more than welcome to. Otherwise, I will see you on Wednesday.